Hello everybody. This is Friday's class where we're going to go through the ACC for 8.1. If you're just starting with us, please pause the video and give this ACC a try and then come back to us when you're done. All right, let's go over it. So in logarithmic form, whoops, oh my goodness, that's no good. I don't like that. Let's put that to a smaller dot. There we go. The logarithm of 2 being, or 12 being the base, 144 is equal to 2. And again, the way I read that is, if I was multiplying together 12s, I'd get to 144 in 2 steps. And that's the way I think about it. All right, now, let's go backwards. This is 11. Come on, you. Come on, pen. 11 to the power of y is equal to x plus 3. For number 3, evaluate. So I'm going to let that equal to x, and then 1/3 to the power of x is equal to 27. So, okay, so what does that look like? Well, here's what I know. Oh, got a question? Somebody's got their mic on. Do you have a question? No? Okay. All right, so now here's the way I would do this. I would change that 1/3 to 3 to the negative 1. And I would change the 27 to 3 to the 3. And then I'd make a new equation where I know that I have negative 1 times x, which is negative x is equal to 3, so x is equal to negative 3. That's not the only way to approach a problem like that, but that's the way I would do it. Okay, any questions on how I did that? All right, now this one's set up as an equation for me, and this time I have x to the power of 1/2 is equal to 9. You can switch that to radical form if you like. Square root of x is equal to 9. So square both sides of the equation, and x would equal 81. And there we go. There's our ACC. So from there, again, let me go to the blog and kind of show you what the plan is for today. From there, we are going to go to we're going to see if anybody has any 8.1 questions that they want me to kind of look at, because you tried them and you got stuck. And then we're going to go through lesson 8.2 in the graphing booklet. Remember, I've split the chapters 7 and 8 into kind of 2 parts: the algebra and arithmetic parts and the graphing parts. And I even put them in 2 different booklets. So yeah, so that's where we're going next. So let's go to the homework. Is there anything from the 8.1 assignment that anybody tried and they'd like me to kind of talk about it or discuss it? If you're not quite done all of this, you can kind of get caught up on it on the weekend, because you're not going to get any new assignment homework. You're just going to have some videos to watch as your homework this weekend. So does anybody have any questions from here that they want to talk about or discuss? Going once, twice. I can ask again on Monday. All right. Nobody's saying anything, or nobody's putting anything in the chat. So then.
Actually.
Oh, actually? Okay, yeah.
I have a question.
Which one?
I could not solve like anything from 3.
All right. So let's do one from 3.
Oh, 3 is in the chapter 7 and 7.3, sorry.
Oh, in 7.3. Okay. All right, let's back up to 7.3. So number 3. Okay, I did kind of B and C the other day. So let's do one. Let's do A. Okay, so let's just cut and paste A here a little bit. New. Oops, that didn't work. New. There we go. And let's just move over here and put that. Paste. There we go. Okay. All right, so the key here is I have to make an equation where the left and right sides are expressed in the same base. And I look at this and I go, oh, okay, well, this base here is clearly 3. And the base over here, well, this right now is the base of 27. But I know 27 is 3 cubed. So I'm going to replace that. with 3 cubed. So basically I've substituted 3 cubed for this 27th. And anytime you do a substitution, you should have learned this way back in grade 7. I'll bet they've taught you this since junior high. When you substitute something into an equation, you replace a variable with a number or vice versa, it's not a bad idea to always put a bracket around it. So now you can kind of see the two exponent laws from grade 9 at work. This exponent here and this exponent here, and it probably looks like I highlighted empty space, but remember, 3 means 3 to the power of 1, right? So those two exponents there are going to add together because you're multiplying together two powers that have the same base. So that's 3 to the 4x plus 1. Here, these two powers are going to multiply because that's the power law of when you take power of a power. So this is going to be 3 to the 6x. Now I can make myself a new equation. This base to that power is equal to the same base to this power, so those two powers have to equal each other. Does the logic of that make sense? So then I'm going to minus 6x from both sides, minus 1 from both sides, divide both sides by -2, and there we have it. X is a half. And you can, just like any other algebra that you solve in your math career, you can verify your solutions. 3 to the power of 4 times a half times 3 should equal 27 to the power of 2 times a half. Well, 2 times a half is 1, so that's side's 27. And on this side, 4 times a half, 2 goes into 4 twice. So this is 3 squared times 3, which is 9 times 3, which is true, so that's correct. Everything in number 3 works just like this. You're going to compare both sides of the equation and get them to eventually one base that's the same on each side. So now that you've seen me do A, give B, C, and D another try. Okay? All right, any other questions?
Okay, thank you.
You're very welcome. Anything else from 7.3 or 8.1 that you want to ask about, guys? Or else let's do some graphing. All right, let's roll on and do some graphing. So here's what we're going to do. We're going to go to the booklet that I gave you that says graphing booklets. And remember, we did 7.2 already. We graphed exponential equations. Right, this book here. So this is the book I want you to get to. So I'll give you a sec to get that book out. And we already did the 7.1 and 7.2 lessons where we graphed exponents. Now we're going to graph logarithms. So go to the lesson that says 8.2. I'll give you a second to get there. Okay, now let's make that bigger. And there we go. Okay, so we are going to sketch the functions y equals 3 to the x and y equals log to the base 3 of x. And the way that we very often graph things is we make ourselves a table of values. So I'm going to make a table of values for this one. I'll do this one in blue. So in blue, this one's going to be, so y is equal to 3 to the power of x. So I'm going to pick numbers that are easy to graph. Like, how about 2, 1, 0, -1, and -2. All right, anything to the power of 0. What's 3 to the power of 0? 1. So we go through there. 3 to the power of 1 is 3. 3 to the power of 2 is 9. So when x is 1, I jump up to 3, and I already know that 2 is way up here at 9, somewhere up on the top of my screen. So how about -1, though? Does that make negative numbers? No, it doesn't. 3 to the -1 makes a third, right? Negative exponents make reciprocals. That's such an important idea. And 3 to the -2 makes -9. There we have it. Okay? Or -9, sorry. I meant to say -1/9. There we go. There we have it. So where's a third? Oh, I don't know. About there. Where's a ninth? Well, it's pretty close like that. And that gives us a pretty good idea as to what we've got happening here. We've got ourselves an exponential curve. It's like, oh, you know what? I've probably need to exaggerate that a little more. It goes up very sharply. And there's people who go, is that like a parabola? Like from if I were to pick, say, this bottom point and cut it off, does that make like a half a parabola? And the answer is no. This is its own type of shape. It's not a parabolic curve, it's an exponential curve. All right, now in black over here, let's do log to the base 3 of x. Now remember what log to the base 3 means. It means we're repeatedly timesing together 3's to make this number, this x number. So for x numbers, I should pick numbers that I know I can count to by skip multiplying 3's. So I would probably pick numbers like 9, 3, 1, and remember you're probably thinking, wait a minute, if you multiply together 3's, how do you get 1? Because remember, if you have 0 for an exponent, you get an argument of 1. And then maybe I'd pick 1/3 and 1/9. Notice I'm basically picking the numbers from this column over here. And y is, of course, at this point maybe you remember, oh yeah, we learned this in notes yesterday. This is really the inverse function of that. So this y turns out, and I just realized I didn't actually label x and y over here. Sorry. This y turns out to be whatever this x was. Right? Log to the base 3 of 9 makes 2. Notice that these things are exactly the inverses of these things. X and y switch spots. So this is -1 and this is -2. So what happens when we graph that thing? Well, 9, 2 is a little off my grid, but x is 3, y is 1 is right there. X is 1, y is 0 is right here. X is 1/3. Y is -1, maybe about there. And x is 1/9, which is pretty close to here. -2 is about right there, which makes this curve here. Something like that. And you should recognize those two graphs as inverses of one another. In fact, if you had put the line y equals x, it acts as a reflecting mirror for those two functions. So there we go. Note, the graph of y equals log to the base 3 of x has a vertical asymptote at x is equal to 0, right? Vertical asymptote, so yeah, that's right here. This is an asymptote. The y-axis is an asymptote for the log, the same way the x-asymptote was, let me say that better. The y-axis is an asymptote for the log graph, the same way the x-axis was an asymptote for the exponential graph. Okay, cool. Next. Let's sketch a couple graphs here. Log to the base 2 of x, log to the base 4 of x, and then log x. Remember, we learned yesterday, that means that the base here is 10. So this, I might even kind of take the time to kind of make this, oh, wait a minute, I want black. Make this go a little longer. And let's see, 7, 8, 9, 10. Okay, so the reason I need 10 is because I can tell that C won't even have an easy time of graphing unless I get as far as 10. But what do we notice about these graphs? I'm going to do them in 3 different colors. I'll do the first one in black. Log to the base 2 of x. Oh, hold on just a second. I'm just going to pause my video here and talk to a colleague. I'll be right back. Sorry about that. Can everybody hear me again? All right, back to my lesson. Okay, so I'm going to do the first one in black. So log to the base 2 of x. So let's start with x being 0. Oh, x can't be 0. So that makes this thing an asymptote, right? Multiply 2's together. How many of them does it take to make 0? You'll never get 0, so that's an asymptote. So how about, for example, what happens when x is 1? Well, then that's when y is 0, right? Because log to the base 2 of 1 is 0, because 2 to the 0 makes 1. And then what happens, what's the next place where I'll have a dot? Well, how about at 2, right? Log to the base 2 of 2 happens when y is 1. When's the next place I know I'll have a dot? If I'm multiplying 2's together, what's the next place that I'll have an integer amount? Aha, it'll be 4. 4 will happen when y is 2. And 8 will happen when y is 3. And then if you want to get fancy, a half will happen at -1. and a quarter will happen at -2. And I think you get this. I guess this would be an eighth. There we go. Oh, that's a good curve. I'm liking that. That's one of the best curves I've drawn today. That is the best curve I've drawn today. I'm quite proud of that. That's a good curve. Okay, next, I'll do this in a blue. So what's this one saying? So think about this one. 4 to the power of 0 is 1, right? So that means when x is 0, y is 1. So it still goes through this point. So there, that point is now black and blue. But the next place that I know I'd have an easy to graph point would be when x is, let's see, well, how about when 4 to the power of 1 makes 4, right? So when x is 4, y is 1. And 4 to the power of 1/2 is 2. So when x is 1/2, right? No. X is this, hang on. This is the exponent, sorry. When y is 1/2, that's better. When y is 1/2, x would be 2. There we go. And let's see, what else would I know on here? Well, obviously 4 squared is 16. That's way too far over. So how about let's do another fraction here. How about 4 to the power of 1/4? That's actually that's terrible. 4 to the power of 1/4. That actually should be something you could figure out in your head, because you can think of that as 4 to the 1/2 to the 1/2, and the square root of 4 is 2, and then the square root of 2 is about, you should know the square root of 2 is about 1.4, right? So anyway, you get the idea. So, oh, let's do some negatives. How about that? That's easier to graph. How about 4 to the -1? What does that equal? That equals 1/4, right? So when x is a quarter, when x is 1/4, y is -1. So 1/4, -1, so maybe about there, about halfway between those 2 points. Good enough. You know what this shape is from here. So I think I better label these. So this guy is y equals the log to the base 4 of x. And this guy is y equals log to the base 2 of x. Okay, so based on how that's going, what's your prediction? I'll do it in green here. What's your prediction for the way C is going to go? Now that you've seen me do A and B. What are you thinking? Hopefully you see the pattern here. It's still going to go through here, because again, 10 to the power of 0 does make 1. But it's going to be flatter this way and steeper that way, if that makes sense. First, let's explain why to the right it's flatter. Because to get to the next kind of integer number, 10 to the power of 1 makes 10, right? So when x is 10, y is 1. So there we go. So there's that part of the curve. Oh, geez, that's a terrible drawing. That should not have gone over the line. Hang on. Something like that. That's supposed to be a curve, by the way. And then it changes directions here, but why is it steeper or closer to the asymptote faster over here than the other two were? Well, because think about it. 10 to the -1 makes 1/10. So when x is 1/10, which would be like way over to the left, that's when I get to -1. So I'm going to get something like that. Does the logic on that make sense to everybody? That's how log graphs behave. All right, notice that all of them pass through the point 1, 0, because again, any base to the power of 0 is 1, except for 0 itself. But 0 can't be the argument of a log, so we're not going to bother graphing that anyway. Or sorry, 0 can't be the base of a log, I should say. So we're not going to graph that anyway. Or it can't be either. It can't be a base or an argument of a log. Okay, so there we go. There's there's our graphs. Now, let's do some sketching. So, what is my parent function or my base function? Well, my base function, my parent function is y equals log to the base 5 of x, which looks like what? Let's graph it. Well, let's see. It's kind of too bad I have such a small scale here. I do have to at least get to a 5. Let's make that at least go to a 5. There we go. Tack a 5 on there. Okay, so let's see. Let's graph this. So what's this going to look like? So when I know I go through this point here, because I know that 5 to the 0 makes 1. All right? And then the next place that I know I'll go through is 5 to the 1 makes 5. So I'm going through this point here. And then 5 to the negative 1 is 1/5. So 1/5 of the way over. I don't know if that's about a fifth or so. Does that look reasonable to you? So I'm going to actually put those down as points now. So I have the points 0, right? X is, 1, 0. When x is 1, y is 0. 5, 1, and 1/5, negative 1. So there's the 3 points that I've just graphed. And there's my parent function. Now I'd like to graph this guy. What's happening to this function? So let's see. Let's jot that down as some instructions here. Well, we don't have any stretches happening, but we are going to shift this graph 2 units to the left, right? How come it's a left? Because it's a plus. And 1 unit down. Is that reasonable for everybody? Is that making sense? So I can take those 3 points and just say, okay, well, if I go 2 to the left, that's negative 1. This was a 1, and I move 2 to the left, so I take 2 away, and it's negative 1. And if I shift 1 down, it becomes that. So this point here, this 1, 0 point that I kind of started with, is now over here. And 5, 1, which was this point way over here, where does this guy end up? Well, if you shift him 2 to the left, 5 becomes 3. Right? And if you shift him 1 down, it becomes 3, 0. So 3 over, none up. So we hit there. And my other point, the one that was the closest to the asymptote, was 1/5, negative 1. So if I take 1/5 and I move that 2 to the left, well, that's like 1/5 minus 2, which I can think of as negative 1 4/5. So I'm going to write that as negative 1 4/5. And then 1 down, well, I was already at negative 1, so if I go 1 down now, I'm at negative 2. So negative 1 and another 4/5, and then negative 1, negative 2. So I'm thinking about there-ish. Okay? And I do have, I'm going to say, vertical asymptote, and then I'm going to misspell asymptote, sorry. Vertical asymptote is x equals negative 2, right here. You can kind of see it from the way that the dots are going. I guess I should finish my curve now, eh? Something like that. There we go. And how do you know, just looking at the equation, that you have a vertical asymptote of negative 2? Remember that because, I'll say, argument of a log cannot equal 0. So that means that this thing here can't be 0. Get it? That's why x can't be negative 2. That's why I have this asymptote. Isn't that cool? So that's how these graphs work. Our domain of this graph is, well, let's see. X can't touch negative 2, and it obviously can't cross it. So x is greater than negative 2. No, equal to, because it is an asymptote. It can't touch it. I might as well put that in set brackets, which I'm never very good at drawing. If you'd rather have it in interval notation, you'd say you'd go -2 comma to infinity. And remember, that has to be a curve because you can't actually touch the -2. The y-intercept, of course, we actually ended up graphing it. We got it right. Oh, no, we didn't. Sorry, we graphed the x-intercept. Oh, so the y-intercept. How do you find the y-intercept? Well, here's your equation, right? I said, come on, you. There. Here's your equation. Y equals log to the base 5 of x plus 2 minus 1. So the y-intercept is going to happen when x is 0. Ooh, so when x is 0. So y is equal to log to the base 5 of 0 plus 2, which means that my y-intercept happens when I have log to the base 5 of 2 minus 1. Now, I can kind of estimate where that is. It's obviously somewhere between 0 and -1, and it's closer to the -1. But how do we figure that out? Well, remember, log to the base 5 of 2 means that in exponential form, 5 to some power is equal to 2. So what is that power? Well, 5 to the 0 makes 1. 5 to the 1 makes 5. So it's going to be point something. And we can guess and check if you like. Is it 0.5? So I'm going to use my calculator. Let me bring up the calculator here again. Calculator. So let's see how close we can get to. Let's see how close we can get to 2. 5 to the power of, let's say, 1/2, which is actually just square rooting it, right? Well, that's pretty close already. 0.5. Let's try, it's a little big though. Let's see what 5 to the power 4 is, or 0.4. 0.4. Too small, but it's somewhere between the two, eh? So how about 5 to the power of 0.45? So 5 to the power of 0.45. Oh, that's really close. Off by 600ths. I'm going to say that's my answer. X is approximately 0.45. So that means I'm going to go here and say, fine, y is equal to 0.45 minus 1, which is -0.55. And that's close enough. And that's about what we got, right? Like I said, a little bit further down than halfway, -0.55 or so. Now you might be thinking, isn't there a way we could get a better answer than this without having to estimate? And there is, and actually that's one of the lessons we'll do next week. It's called the change of base law for logarithms. But we haven't learned that yet. Okay, you want to try one? I'm going to pause the video and let you try one. Now, remember, this is messing with you. I'm keeping my eye on the chat here. Who can tell me what you have to do here before you start graphing anything? Uh-oh, everybody's asleep. Nobody? Come on, somebody knows. What do we have to do with that thing first? Remember, it has to kind of look like this, where that's my vertical stretch. And this would be my, oh, actually, this can't be x. This is going to have to be some, I guess I'll use n or something. X minus h plus k. So any ideas what happens here? What do you notice about what this looks like and what that looks like? What's wrong? What do we have to do?
The 3 and x should change places.
The 3 and the x should change places. Now take a look at this. If we just plain old switch them, I guess, oh, you know what? I missed something. I'm sorry. I forgot my b. There should be a b in there. Duh. Sorry. I had a duh moment there. What needs to happen now? Yeah. Oh, well, A's over here. Yes. Somebody in the chat just put the b is -1. How do you figure out that that b is -1? What do you do? What operation do you need to perform on this to get to there? Factoring is correct. So you are going to actually graph this. Y equals log to the base 3 of negative, I'll put another bracket, of negative x minus 3 plus 1. So my parent graph is log to the base 3 of x. And then what am I doing to it? I am reflecting it. Which reflection is it when b is a negative? I'm reflecting it in the y-axis, and then I'm shifting it 3 to the right and 1 up. So I'm going to pause the video and let you play with that for a minute and see if you can get it. Okay? Somebody just pointed out to me that when I said plus 1 is 1 down, that was wrong. It should be 1 up. So let me say that again. Graph this, and then what you're doing to it is you're reflecting it in the y-axis, shifting 3 to the right, and shifting 1 up. Thank you very much. Okay, now try it. Okay, hopefully you gave yourself enough time. Here we go. Let's graph this thing. Okay, so I'm going to graph the parent function first, and then I might even pick a few points and use mapping notation to make sure I do this right. So log to the base 3 of x. So let's see, what points do I know are on log to the base 3 of x? I know that when x is 0, or sorry, when x is 1, y is 0, right? Because why do I know that? Because I know that 3 to the power of 0 is 1. So I go through there, right? So there we go. And then I know that 3 to the 1 is 3. So that means that in logarithm notation, that when x is 3, y is 1, right? Because log to the base 3, in other words, I could write it down as log to the base 3 of 3 is 1. So there we go. Log to the base 3 of 3 is 1. There. Then I might do one more point. Let's do one where we're approaching the asymptote. We know that we can't touch the y-axis. So let's see what happens when we have an x of, say, 1/3 would make -1 for y, because log to the base 3 of 1/3 is -1. Or in exponential notation, base 3 exponent -1 argument 1/3. So there we go. There's our points that we're going to graph. So 1/3 over, 1 down. And that's my parent function. Okay. Now, we would like to take those points and what are we doing to them? We are reflecting in the y-axis. So when you reflect points in the y-axis, the point 1, 0 now ends up flipping over to -1, 0. So I'm going to take this point. So let's see, I need some more room to work. I'm going to work over here. So I take the point 1, 0, and then using mapping notation, I reflect it in the y-axis. So that means the x that's 1 now becomes -1. Okay, what am I doing to it now? Now I'm shifting it 3 units to the right. So I'm at -1, but if I move 3 units to the right, I'm at +2. Then what am I doing to it? Then I'm moving 1 up. So I get to the point 2, 1. So this point here that started as 1, 0 ends up being 2 over and 1 up. Ends up being there. Okay. While I'm at it, let's kind of get a sense of which direction things are going to go. Where is my asymptote? Well, remember, this thing can't be 0. So I have a vertical asymptote of x equals 3. So there is my vertical asymptote. So it makes sense, right? The parent function's going to the right forever. This one has the asymptote over here, and it's going to the left forever, which makes sense, right? Because it is a reflection. All right, let's do another point. 3, 1. So I start with the point, I'll work over here. I start with the point 3, 1. What do I do with it? 3, 1 gets reflected in the y-axis, so the x value is now a negative. Then it gets moved 3 units to the right, so that's actually going to take that to 0. Then it gets moved 1 up, so it's going to be 0, 2. So 0, x, and 0, 2. There we go. Right? And one more. This is kind of the toughest one because I got to work with a fraction. I'll do it over here. We start with 1/3, -1. Okay, so the x values become their opposite because we're reflecting in the y-axis. So -1/3, -1. That's supposed to be a negative, but I didn't draw it very good. Negative. There we go. Then we are going to shift it 3 units to the right. So if I'm at negative 1/3 and I go 3 units to the right, I'm at positive 2 2/3. Let me just make sure I got that right. Yes, adding 3 to negative 1/3 is 2 2/3. Then I am going to move 1 unit up. So I have 2 2/3, comma 0 is where I'm going to land. So this point here is going to move to 2 2/3, so about there, comma 0. So 2 2/3, so about there, comma 0. That look reasonable? And there we go. I think I can see where we're going from here. So to the S. I don't like that line. I don't like that. I'm going to do that again. Yeah, good enough. There we go. Got a little bit tumoury there down the side, but it'll work. Okay, so there we go. Now let's talk about this graph's characteristics. What's its domain? Well, my domain would be, again, in set notation, x has to be less than 3 because we're going to the left and we can't touch x as 3. Or if you like that in interval notation, we're going from negative infinity to 3. My range, what do you think? What about range? Well, I know that you're thinking this thing's going leftward, but it's also going upward. Is there anything that's going to stop it from going up? No. Anything that's going to stop it from going down? Nuh-uh. Oops. Y can be any real number you like. Or that. Right? That's infinity, sorry, being scrambly. Okay, what's my intercepts? All right, let's do some algebra on this. They don't give me a whole lot of room. I'll have to write small. So my x-intercept happens when y is 0. So 0 equals log to the base 3 of 3 minus x plus 1. Okay, so let's see. What's that going to be? So I'm going to move the 1 to the other side. It's now negative 1. Okay, and let's see. Now I'm going to switch to exponential equations. So base of 3, exponent of negative 1 equals my argument of 3 minus x. 3 to the negative 1 is a third. And then move the 3 to the other side. I get negative 2 2/3 equals negative x. So x is equal to 2 2/3. So there it is. There's my x-intercept, 2 2/3, which I kind of knew. That was one of the points we graphed, wasn't it? Right there. Y-intercept. I'll solve that over here. So y-intercept happens when my x is 0. Okay, so let's solve that. So that means y equals log to the base 3 of 3. And anything, this is actually going to be true, log to the base x of x is always going to be 1. Why? Because x to the power of 1 is itself. So log to the base 3 of 3 is just 1. So that's going to be a y-intercept of 2, which is right there. Okay, so even if I hadn't graphed it, that's pretty easy algebra to do. And the equation of the asymptote again. How do I get the equation of the asymptote? I look at my original equation and go, argument can't be 0. What makes this argument 0? 3 does. So x equals 3 is my asymptote. And there we have it. That's graphing. Yeah, it does. You're right. It does kind of give you both the intercepts, especially when you graphed it. But say, for example, I gave you a question. I'm not going to make you graph this, but it is a perfectly reasonable question that I might give you where I say, if you graph this, find me the x and y intercepts. And you're going to just use algebra to do it. Okay? Does that make sense? So I won't make you graph one of these on the test, but finding asymptotes is fair game because you can just use algebra to do that. Okay. That is it for that little lesson on graphing. I might get you, I think maybe on Monday we will get you to do the 8.2 ACC. I'll let you use your notes just to make sure you can do it because the curriculum says we're supposed to cover it, but I'm not going to test it. Okay, so we'll do the ACC just to kind of keep you honest to make sure you can do it. And then we're going to move on Monday into the 8.3 and 8. I'll probably get the 8.3 lesson done Monday. Then we'll need a few days. We'll probably spend the rest of the week doing 8.4. People right now are kind of hastily flipping through the book. What the heck's so crazy about 8.4 that it's going to take several days to do it? And then you're going to look at it and go, oh yeah, there's word problems. This applications of logarithms are incredibly important if you have any hopes and dreams of a STEM career, because all of the sciences use logarithms to help them solve things when the algebra and the arithmetic gets oogly. So we're going to explore word problems probably for a couple of classes. We'll also probably give you at least, we'll give you some work time as we get into that as well. So if you're caught up on everything, you're homework free for the weekend, but I did put on the blog that if you're not caught up on everything, of course, go back and work on the 7.3 and 8.1 worksheets. If there's people going, oh, 8.1's assignment, I'm finished it, but I really could use more practice, I'm going to update this blog post and I'll put an optional worksheet that you can download and work on if you want just more practice on 8.1. Remember that you can always go back to the notes booklets, and we still have the textbook assignments at the end of every chapter, right? So if 8.1 was not your friend as you were trying to do your homework, this is 8.1, isn't it? Yeah, it is. If 8.1 was not your friend as you're trying to do your homework, there's always extra practice that you can get from your textbook. But Ms. Bednarski put together a really cute little worksheet, so I'll put that on the blog too. I'll make it optional. If all of the questions in 8.1 are easy for you, we don't want to waste your time or anything. But if you want more practice, it's there. And the other thing, of course, is I do have these 3 videos. I tried to pick ones that I think are really interesting. This one especially about why logarithms were invented in the first place. We've kind of come a long way from where logarithms were actually invented to help people do math in the days before you had even basic adding machines. So this is actually a really, really interesting video. And then coming up later on in this chapter, when in 8.4, I think, we're going to be introduced to E. E is a really important number in math, and the guy who explains it in this video explains it better than anybody I've ever seen explain it. So this is a good video for that. And then if you've ever seen a Weihart video, those of you who had me back in Acadia, if you had me for grade 8 in Pythagoras, I'm sure I showed you Weihart's Pythagoras video. Weihart is a genius. She's hard to follow. You might want to watch her video almost on slow speed, but she is extremely entertaining. And she has a really cool way to think about logarithms. It's actually similar to the way I think about logarithms as skip, multiply, counting. But of course, I can't explain it the way she can because I'm not a genius. So those are basically your homework for the weekend. If you would like to log out and start your lunch a few minutes early, go right ahead. I've already done attendance. Have a good weekend. All right, I'm going to stop the video.